We are going to look at finding the projection of a vector onto another vector, and I've got a graph here of what we're looking at. I want to look at the projection of vector m onto vector v. So I have these here, I have the components listed, and then over to the side I have the formula that we need to use. Inside the parentheses I have a dot product. In the denominator, I have a magnitude squared. So this actually could be rewritten as a dot product over a dot product, since we have a rule that tells us that the dot product of a vector by itself is the magnitude squared. So we can look at a modified idea of this formula. I'm going to do a couple of side calculations before I start to apply this formula. So the first calculation that I need to look at is vector m dot vector v, and then I need to look at vector v dot vector v. So this top calculation will end up being the numerator, the bottom calculation is the denominator, and then we have to multiply that number that we get here by this vector here. So essentially we're going to end up with a scalar here, multiplying this vector out to the side, and that's going to be a new vector, which is kind of the idea of a shadow being cast from one vector onto the other. That's kind of what a projection is. So let's look at these calculations. So I need to do dot product. I have the first term of m, which is -2, times the first term of v, which is -3, plus the second term of m times the second term of v. And so I end up with negative times negative is a positive, so I have 6 plus -6 here, so I have 0. So that means that this is orthogonal. Whenever we have a dot product of two vectors that gives us a 0, that means they're orthogonal, which means that we know this is 90 degrees. That's going to have an interesting result here in this formula. If I put in 0 in this numerator, that means the whole fraction is equal to 0, and so I will have 0 as a scalar on this vector, which means I'm going to end up with the 0 vector for the projection. So I really don't have to go through with this calculation at all now, since I've recognized that my two vectors are orthogonal. This really breaks this projection down so that I have the projection of vector m onto vector v is going to be the 0 vector. So we are done there. Alright, so we probably want to look at another example of this so that we can see some more of the pieces interact with each other when we don't have something that meets at 90 degrees. But this is a nice example to see what happens when you do have two vectors meeting at 90 degrees. The next example I'm going to look at is the same v vector, but we're going to look at a slightly different vector m. It's just a little different from the original. And so again, we need to look at a couple of calculations. We need to look at the dot product of the two vectors that we have, and then the dot product of the second vector by itself, so that we can plug it into our projection formula. So we're looking at -3 times -3, and then we're going to add that to -2 times 3. And so we're going to end up with a +9 plus a -6, and this is going to give us a +3. And now we're going to look at this vector by itself. So this is going to be 3 squared plus 3 squared. The negative squared is going to give us a positive, so we're looking at 9 plus 9, which is 18. So now our projection formula, we're still trying to answer the same question, the projection of vector m onto vector v. So we're looking at vector m with respect to vector v here. And so we have vector m, vector v over vector v, dot product vector v. And then we're going to use that as a scalar on the vector v. So filling in the numbers, I have 3 divided by 18, and that's going to be multiplied by vector v. So I have this calculation. So you can reduce this fraction. You can make that 1/6. And then this is a scalar times a vector. So it's kind of acting like a distributive property. So you're going to end up with negative 3, 6, 3, 6. And then those are reducible. So we have the vector and component form of negative half, half. And you can assign a new vector name to this. So perhaps you want to label this one vector W. This is our vector that we get when we project vector M onto vector V.